Hey, what's up, guys? Yeah, so this video, let me talk about the classical geometry, like straightness and the compass. So basically, this video try to explain how to your elementary school, junior high school, that you learn how to use a ruler and the compass, which basically you can draw a circle with certain radius, and you can ask whether one number is constructible or not, and there are some problems. So basically, this is a standard application use the mathematically called field theory, which is not the same as physicists called field theory. Right, this field is a mathematical. You have a field which you can do the plus, product, and the division is non-zero, and do the minus. So basically, I will introduce the constructed number and the previous field and the US field extension, and I will explain the Egyptian the three problems, basically why people cannot do pi, why you cannot double the cube, and why you cannot trisect the angle. So basically, these three numbers are not constructible. So basically, you cannot use complex and rulers to construct such numbers. And also in the next video, I will prove the Gauss theorem, basically a unregular, in what case that you can construct an unregular polygon. So the famous results is that people can draw a pentagon. I think go back to 2000 years ago by some Egyptian. So basically you can construct this because sine 15 is the square root of 5 minus 1 divided by 4. So this guy is constructible because you can construct square root of 5. And also the famous result is that the 7 regular gun or septagon is not constructible. And the famous results proven by Gauss is this 70 gun, which you can 17 regular gun can use in the can be used ruler and the compass to do this. And more formally, you can prove that an unregular gun is constructible if it is the 2 to the power times the distinct Fermi price. So this is the largest theorem that you can classical 200 years ago that people use field theory and the Galois theory. So there will introduce, you will need some basic background of Galois theory. And but I think this all of this except for the final one can be understood using the standard field theory. Hope you guys subscribe to my channel. Okay. So let's start. Okay, so let me just give a definition, right? So our idea is that we are working on a plane where it may be R2, and you have a standard distance which is 1, right? So basically you need to some fundamental ruler. Right, so basically you have some fundamental distance and you have a ruler. The idea is that ruler has no points on it, right? Otherwise that you can do other things. And then also you have a compass, right? So compass can draw any circle, but with the radius that you already know. Okay. So the idea is that all the numbers, let's say in R, can be done by finite move of ruler and this compass. So basically ruler, any 2 points you can connect it with ruler, okay, are called the constructible number. So basically so what I'm saying is that I use a real number, but you can also give the definition of the complex number, and this is very simple, right? Because in a 2-dimension, if let's say this is P1 and the P2, you can easily say that if P1 is constructible and the P2 are both constructible, then you can construct this, right? Just draw P1 here and draw P2 here and connect it. So a number in the complex number is constructible if and only if both x and y coordinates are constructible. So talking about reals are already enough to give the complex number. Okay, so for example, by definition, 1 is constructible, and the 2 is constructible because you just plug 1 and plug another, right, which is 2. So any integer is constructible. Okay, and not only that, you can easily prove the following. Okay, so theorem. Let me use this C to denote all the constructible number. Okay, so C is a subset of R, which is in our case. Okay, here C is not just the subset of R, so C is a field of R. C is a subfield of R. Okay, so all you need to prove is that if alpha and beta are constructible, then their sum are constructible. If alpha and beta are constructible, then their product are constructible. Also, their division is constructible if beta is non-zero. Okay, also the final one, which is not usually in the field, but in this case, that the square root of alpha is constructible if alpha greater than 0. Yeah, basically, you can just discuss the number greater than 0, right? Because it's negative, you just flip it. Okay, so proof. So this is very simple, right? This is your elementary school, right? So let's say you have some length alpha and you have a length beta, right? Then alpha beta is alpha plus beta is constructible because you can use the ruler, right? So say alpha and you use the ruler to extend it to beta. This is alpha plus beta. Okay, and the difference is constructible, right? Because let's say alpha greater than beta, then this is alpha. You just use your compass and draw beta, right? So these lengths will be alpha minus beta. You can use a compass, right? And also in this one you can also use the compass to draw beta. Then these points will be alpha plus beta. Right. So basically you can start from this and draw beta. So it's here. So alpha plus beta. So this one are trivial. Okay. How about alpha times beta? This is also trivial, right? Because you have some basic similar triangles, right? So let's say this is 1, and I can construct alpha. And if I do this, I put beta here, then you can extend it. Then these lengths by the similar triangles will be alpha times beta, right? Because beta divided by 1 is beta, alpha beta divided by alpha is beta, right? So they are the same ratio, right? So you just need to use the similar triangles. Okay. Also, alpha divided by beta is also trivial because I already proved that you can just write as alpha times 1 divided by beta. So you just need to prove that you can construct 1 over beta, which is also trivial because there's a 1 here, right? And let's say this is beta, then you can just do the same thing. You can say this is 1. I can construct 1 and I extend it. Right, then this guy should be 1 over beta. Okay. Because this 1 over beta divided by 1 is, I think it's the 1 divided by beta. Okay, and yeah, so basically we already proved this. How about the square root of alpha? Okay, so this is probably the only a little bit non-trivial one, but hopefully you learn about your high school. So this is 1. Let's say this is alpha. Then you can in here and draw a circle, and then extend this line. Okay. So this will be alpha plus 1 divided by 2, and then you draw this. Okay. So your high school mathematics will teach you these lengths is a square root of alpha. Okay, so if you cannot see it, then there's this right triangle, right? So let's say this is x, so x, let's say this is theta, so x divided by 1, which is tangent theta, and this is also theta, right? It's the same as 1 divided by x. 1 divided by x is tangent theta, and x divided by alpha is tangent theta. So x squared is alpha, so x is a square root of alpha. Okay, so this is what we prove. So we prove that all the constructible numbers are not just a field, not just a subfield, but also contain some strange operations that which you can take a square root. In general, it's not field. It's not trivial. Okay, so basically from this I can prove that all the rationals, right, become the subset, and then not just rational, right? Square roots become a subset. right? So basically, I can prove that the Q adjoin the square root of 2 as a field belongs to subset, belongs to this constructible number. So this tells you the constructible number looks very large. Okay, but how to systematically research this? So for example, this field, right, also belongs to constructible number, right? Because this is just square root of it. So now now we need to do some work. Okay, so let's do some do this observation, right? So each line, let's consider our originally working is some field f, and then we are looking at the constructible number over f. So we have a line. Let's say we have ax plus by equals to c, right? And then suppose we have another line. Now this intersection point must be the linear combination or of this ABCD. Right, so given any two lines, these points are also in F, right? Suppose the coefficient of the line in F, then this point will still in F. Okay, but if you have a circle, right? Let's say you have two circles. Let's say the radius coordinates and the radius and the origin are both in the field F, right? So let's say R is F, and all the coordinate X and Y are in F. Then this, if you use these two circles and their difference will give you another line. And this line and this circle will have intersection, right? But this is a quadratic equation. So the key idea is this. So you can see that this is a quadratic equation. So which tell you that, let's say these points can be constructed called gamma, okay? Then what you have said is that, this you can take this gamma, right? So this gamma is basically some equation of quadratic. So which tell you that gamma belongs to a field extension of F with degree 2. Okay, so which tell you that if you start from field F, then this point must belongs to another field extension, right? So but with degree 2. Okay, so basically you draw one circles and you draw a line which you can add these two roots into a field. Let's say you add these two roots. This is the same as you only add one root, right? Because they are the same. There are difference basically in F, right? So basically, let's say you adjoin this gamma and with the original field F, then this dimension will be 2. Okay, so now we can start from F, and then we can start from F square root of gamma 1, and do the square root of gamma, adjoin gamma 1 and gamma 2, and keep going. And each guy has dimension 2 or 1 or 1 or 2, right? Because you can use a circle, you can use a compass or a line. Okay. Okay, so we have the following. Point is constructible from F if and only if there is a lambda 1, lambda n, which is in real number, such that the first one is that this F adjoin with this lambda 1 with F is like either 1 or 2. If you only use the ruler, then it should be 1. If you use a circle, it may be 2. Okay. And the second is that F lambda 1 adjoin with lambda 2 up to lambda I compared to the previous one up to lambda I minus 1 must also be 1 or 2. Okay. So now we have the criterion for constructible number. Okay. Okay, so now we have our theorem, which you can use. So this is the main theorem that I want to prove. Okay, so this theorem can give us a various example that which one is constructible, which one is not. Okay, so theorem. So let's say alpha belongs to some real number, and alpha is constructible if and only if there is this lambda 1, lambda n, which is a real number. such that the alpha belongs to rationals, right? Because we starting from somewhat, right? We have some basic length scale, lambda 1, lambda 2, up to lambda n, such that the lambda 1 square, right? Lambda 1 square is a degree 2, right? So lambda 1 square must belongs to F, or in this case belongs to Q. And lambda I square belongs to Q, lambda 1, lambda 2, up to lambda minus 1 for I from 1 to n. Okay, so this is the proof, basically for our proof. Okay, so from the previously, we get two results, right? So remember this field extension has the formula that let's say this lambda 1 up to lambda n with this f can be written as a f lambda 1 up to lambda n, and f lambda 1 up to n minus 1 times f lambda 1 to n minus 1, and f lambda 1 to n minus 2, and finally become f lambda 1 and f. Okay, so this is the field theory result, right? So this basically is 1 or 2, right? So basically we prove that any extension, so this f1 lambda 1 up to lambda n over f must be 2 to the power. Okay, so theory. Alpha is constructible if and only if alpha lies in some field, alpha lies in, let's say, f of something, or basically you can say that f of alpha over f must be what? 2 to the power. Okay, so this is very important. A constructible, the number is constructible if you add join with, if your original field f, then become its field extension is 2 to the power. Okay, now this is the same as the irreducible polynomial, the degree of irreducible polynomial over f with roots alpha. Okay, this is field theory results. If you haven't seen it, I will post my field theory lecture. But basically, you just ask what is the smallest degree, which is a proof be an irreducible polynomial if field f is characteristic 0, and then it's root alpha. Yeah, it's root alpha. The degree of this polynomial is the same as f alpha adjoint with f. So if it's 2 to the power, then it's constructible. If not, it's not constructible. Okay, so that means that if the degree of irreducible polynomial, irreducible polynomial of alpha is not 2 to the power, then it is not constructible. Okay, so let's see examples. Okay, so now we have the powerful results. We know the answer, right? The answer is that the field extension is 2 to the power, then it's constructible. It's not. Okay, so we have done this, and then let's solve these Egyptian 3 problems. And in the next video, I will talk about the Gauss results. Okay, so theorem. The first example is very trivial, right? So let's say pi is inconstructible. Okay, the reason is that pi is transcendental. I don't know how to spell. I just forget. But basically, no algebraic equations which can add most pi can fit in pi, right? So basically, no p which belongs to q of x, about p is not 0, such that p of pi is 0. Okay, so this is which I think the Lindemann proof. Basically, the similar problem for E, right? So E is inconstructible, and I have a proof that E is a transcendental. I will post a video link if you are interested. Okay, so second is the square root of 2, which is inconstructible. Okay, because the minimum polynomial of the irreducible polynomial of this guy is x cubed minus 2 is 0. Now this is q of x, right? So if you adjoint this 3 square root of 2 in Q, this is a field extension with degree 3, right? So it's not 2 to the power. Okay, so it's inconstructible. Hey, by the way, this guy is irreducible. You can use the Newton's method, you can check that x equals plus or minus 1 or x equals to plus or minus 2 is not the answer. So which is not is irreducible. Okay. And the third, that's talking about the trisect, the angle. Okay, so you only need to find the angle which is inconstructible, right? But that angle should be constructible. Okay, so let's work in the 60 degree. Okay, so my proof is obviously that 60 degree is constructible, right? The reason is that you can just draw a triangle with the same lengths, and this length is a cosine 60. Cosine 60 is a half, which is constructible. Okay, suppose I want to trisect the 60 degree, then I will need to find the cosine theta such that the cosine 3 theta is a cosine 60, which is a half. Okay, so what is the equation which satisfied, right? So cosine 3 theta is half. Cosine 3 theta is 4 cosine cube minus 3 cosine theta. Okay, so this is called the Chebyshev polynomial. If you don't know it, don't worry. I will post a very small video list of the Chebyshev polynomial if you don't know what is the cosine and theta. But hopefully you know. Okay, so this is what. So let's say you just let x equals to cosine theta. So your equation will be 4x minus 4 to the cube minus 3x minus half, which is 0. So it's ax cubed. Okay, so your exercise is very trivial. You can use the Newton's method and show that this equation, this polynomial is irreducible. Okay. So if you add joins your lovely theta with the q, where degree will be 3, it's not power of 2. So trisect 60 degree is impossible. Okay, so remember that I'm not saying that trisecting any degree is impossible, right? Because you can trisect 180 degree and it can become 60 degree. But for some particular angle that you cannot. Okay. Okay. Before I finish, let's talking about some exam. Let's talking about one things I want to say. Okay. So this thing is that theta is constructible. So sometimes people will not say the angle, right? Will not say the length, but say the angle where 60 degrees inconstructible. So cosine is constructible if theta is constructible if only if cosine is inconstructible. Cosine is constructible. This is the usual language. So when somebody say the angle is constructible, which means that cosine that angle is constructible as a length. So this is as a length. This is as an angle. Okay, the reason is trivial, right? Because you can always draw one dimension. You can always draw a radius one circle. And suppose cosine theta is constructible, right? Then you can put this as a cosine theta. Then theta will be constructible. And on the other hand, if theta is constructible, if and only if cosine is constructible. Okay, so okay. So if you want to solve that, if you want to know why 7 gun, right, 7 regular gun is constructible, then you're asking why cosine 2 pi divided by 17 is constructible. Okay, so in general, if you want to solve the Gauss problem, basically, in what case that irregular gun is constructible, then you need to show that cosine 2 pi divided by n is constructible for which n. Okay. And then I will prove in the next video that the cosine 2 pi divided by n is constructible, which n is related to so-called Fermat prime. Okay, so this is my first video, and this video will be only 2, right? The first one, this one, the second one. Subscribe to my channel. See you guys next videos.